Hi, this is Stephen Brower from Raton Valley Community College. This is the continuation of part one. I know this is another part, but anyway, part two is going to, what I mean by part two, oh God, there's two sets of slides in Canvas. Part two slides go into further depth on shortest path and Dijkstra's algorithm. This is still in part one, although we're in part two of part one. This is just sort of the overview in terms of graphs. And the last slide I left off at was this one as a way of illustrating two possible shortest paths. If we're at vertex 2 and we're trying to go to vertex 0, one way we can go there is by taking this path and we incur a cost along the way. So going from vertex 2 to vertex 3 incurs a cost of 12, and from vertex 3 to vertex 0, an additional 15 for 27. But another path that we can go is vertex 2 to vertex 3 for 12, vertex 3 to vertex 1 for an additional 6, that's 18, vertex 1 to vertex 0, an additional 7, that's 25. That actually has, in terms of these costs, less weight. An aside, by the way, there are other algorithms where they look at the number of edges that are encountered as opposed to the weight. This right here is looking at the weight. But we're still finishing up part one. I know it doesn't seem that way. How do we actually go and implement this on the computer? Well, one way to implement a graph is to use linked lists for the adjacent vertices. Now remember, adjacent is that two nodes are considered adjacent if there's an edge that connects them together. So vertex 0 and vertex 2 are adjacent to each other because there's an edge that connects them together. Vertex 2 and vertex 1 are not adjacent because there's not an edge that connects them together. From vertex 2's point of view, vertex 1 is reachable. From vertex 1's point of view, vertex 2 is reachable, but they are not adjacent. So an adjacency list would just be showing or listing the vertices that for a node that they're adjacent to. So vertex 0, which is this one here, vertex 2, vertex 3, vertex 1, they're all adjacent, so they would be in the adjacency list. Vertex 1, its point of view, 0 and 3 are adjacent. So from vertex 1, it would have 0 and 3. Vertex 2's point of view, vertex 0 and vertex 3, those would be adjacent. And then vertex 3's point of view, it's 2, 0, and 1. Those are adjacent. Vertex 2, vertex 0, vertex 1. So showing more logically how this would look is imagine for vertex 0, which is this one here, and we want to indicate that 2, 3, and 1 are adjacent. So we actually can have a linked list, and the linked list is a linked list of vertices. And so from here we would get these are the vertices that are adjacent to vertex 0. And then for vertex 1, well, vertex 1 is the one that's here. That should be 0 and 3. So then a linked list of its adjacent vertices, 0 and 3. From vertex 2, as I hit spacebar too quickly, vertex 2 has 0 and 3. Those would be in their adjacency list. And then the last one, vertex 3, would have 2, 0, and 1, 2, 0, and 1 as their adjacency. So the singly linked list that we did in Lab 5, which we used again in Project 2, that singly linked list, we could have a singly linked list of vertices. And so then for a vertex, we can have a linked list of vertices that are adjacent to it. So if we want to ask a question, so suppose here we're on vertex 2 and this is our list. We want to find out, is vertex 1 adjacent? So that would be taking a look, is vertex 1, does it exist in this list? So we already wrote the exists method when we wrote that Lab 5. And if we were to implement a graph using our linked lists, then the logic for exists we already wrote. It's just the use of it to saying if vertex 1 is in this adjacency list, does it exist or not? Something I did not point out in the earlier part of point 1, and I should have, is linked list did have a starting point, an access point to the linked list. It did have head. Stack had top. Queue had front and rear. And tree had root. Well, for a graph, there's no top, there's no bottom, there's no front, there's no rear. And the idea is that we usually are asking a question of the graph from a vertex's point of view. So in other words, when asking the question of vertex 2, is vertex 1 adjacent, then we would directly go to vertex 2, which we can access it this way. If we have an array, if we actually have an array of sort of linked lists, as it were, and then each element here would represent a vertex. So element 0 is for vertex 0, element 1 is for vertex 1, elements 2 for vertex 2. But if the question is being asked of vertex 2, is vertex 1 adjacent, is then we would just go here, look at the linked list, and then we would see that it is not adjacent because it's not in the adjacency list. So, then these things are questions that are made of graphs are from a node's perspective. Okay, so another way that we can implement a graph is to use an adjacency matrix, which is a two-dimensional array. And, again, we're adjacency. Remember, adjacent, two nodes are adjacent if there's an edge connecting them. So we're not talking about reachable. We're not talking about can we get to other nodes. We're talking specifically about adjacent, the nodes that are adjacent to one another. And so in a two-dimensional array, the rows can represent the vertices, the columns can represent the vertices, but what we will generally do is that when we're looking at this two-dimensional array, we do it from the rows point of view first, meaning from node I to node J is how we would be looking at that, from node I to node J. A two-dimensional array of Booleans can be used for non-weighted graphs, and a two-dimensional array of, well, whatever we're using for costs. Two-dimensional array of integers, two-dimensional array of doubles. If we have a more complex cost, it can be a two-dimensional array of the cost object. If it's a more complex way of going from one to another. But here, given this graph, which is the same one that we had for the linked lists, so vertex 0, we would say, well, what's adjacent? Well, 2, 3, and 1. So this row represents vertex 0. And this row representing vertex 0, we have, well, here's the 2, there's the 3, there's the 1. From vertex 1's point of view, we have 0 and 3. So vertex 1 point of view, we have 0 and we have 3. Vertex 2's point of view, we have 0 and 3. So vertex 2's point of view, we have 0, so 2 to 0, and we have 3, 2 to 3. And then vertex 3's point of view, it's 2, 0, and 1. So vertex 3's point of view, here we have the 0, here's the 1, and here's the 2. By always using the row as our starting point and the column as our destination, we are looking at from the row to the column being the destination. Now, because there's no arrows on these edges, if we actually kind of look, if we look at the diagonal and look what's above the diagonal and below the diagonal, well, if we have linear algebra, you get into transposing a matrix, and that's kind of what we have, is that the going across the axis. Well, anyway, sorry, let me just move on. Now, what's going on here are two things. One is it's directed, and this is why it's important going from row to column, because like if we're looking at, vertex 2's point of view, so by this row here being vertex 2, the only one that has a value is in for column 3, so vertex 2 is going to column 3. And here, the 0 is representing not reachable. If 0 is a valid cost, we would then have to use something else like maxint, like integer dot maximum int, something like that. But if 0 means it's unreachable, we can then just use 0 as the value. So vertex 2 only has that one value, which is the 12. Vertex 3, it's 15 to 0 and 6 to 1. So vertex 3, it's 15 to 0 and it's 6 to 1. Vertex 1 only has one edge. It's to vertex 0, which is 7. Vertex 1, there's the 0 and it's 7. And vertex 0 only has one edge from it. It's 9 going to vertex 2. And so here's the 9 for vertex 2. So this two-dimensional array of integers can be used for a weighted graph. The nice thing about Java, if we allocate a two-dimensional array of integers, it automatically initializes the elements to 0. If we were using something like C++, we'd have to go in a nested loop and to initialize the values. I'm very good at taking fun out of things, and I'll explain where I'm going. But suppose we wanted to have like a mini adventure game, and we wanted to sort of represent moving around the house. And kind of like if we were physically in this house and we want to go to the study, well, we don't have a transporter. We can't directly access there. If I want to get to the study, I have to go from the dining room to the front foyer to the back foyer to the study. And then now that I'm in the study, suppose I want to go to the pantry and get something out of the pantry. I can't go straight there. I can go into the back foyer, from the back foyer into the kitchen, from the kitchen into the pantry. And now let's say after I get what I have in the pantry, I want to go to the living room. Well, one way I can go is I can go into the dining room, I can go to the front foyer, and now I'm in the living room. So imagine just in terms of a house, the layout of a house is that some rooms are adjacent to each other. Adjacent, see where I'm going? Some rooms are adjacent to each other. So the dining room is adjacent to the front foyer. The dining room is adjacent to the pantry. And other rooms, they're not adjacent, but they're reachable. So the study is not adjacent to the dining room, but we can get there. And actually, not only that, there's more than one way for us to get to the study. So if I were to look at this as being each room being a node, then what I can do is I can actually come up with vertices and say these are the vertices that we have in our graph. And I can establish, okay, here is our graph with these vertices where, and I just arbitrarily pick them, but the kitchen would be vertex 0, the pantry would be vertex 1, the dining room would be vertex 2, the back foyer vertex 3, the front foyer vertex 4, the study vertex 5, the living room vertex 6. So then to establish the adjacency, the kitchen is adjacent to the pantry, and the kitchen is adjacent to the back foyer. So that I'd have an edge going here and an edge going here. When I just fill in all the edges, then this would be the graph in terms of what's adjacent to what. So the living room, the only thing it's adjacent to is the foyer. The foyer is adjacent to the living room, the back foyer, and the dining room. The back foyer is adjacent to the study, the front foyer, and the kitchen. So now, taking this graph that we just come up with, I can create then from it the adjacency matrix. So here's our two-dimensional array of Booleans. And so if I just let me just arbitrarily take the dining room here. Well, all that's adjacent from the dining room is vertex 1 and vertex 4. So vertex 2, here we have vertex 1, here we have vertex 4. So suppose I'm in the dining room and I want to see, well, can I get to the study? Well, the first thing I'll see is that it is not adjacent. So the first thing is it's not adjacent. So if I was in the dining room, I'd have to then look at both from vertex 1 and vertex 4 and figure out how do I get there. There is going to be another video on breadth first search and depth first searches. And so we'll revisit that. Just the final thought in the last 20 seconds we have, how we decide which to use. Dense graphs, the number of edges are closer to n times n minus 1 over 2. These are dense simple graphs. And adjacency matrix are better for dense graphs. Linked lists are better for sparse graphs. I'm out of time.